Bismillahirrahmanirrahim. In this video, we are going to discuss and derive the extension of Lie symmetry generator, and we'll give some example related to the previous video in which we discuss symmetry equation for a function and for differential equations. So what is prolongation or extension of a Lie symmetry generator? You see, we take uh, the transformation x bar equal to x plus epsilon dx bar over d epsilon at epsilon 0 plus up to so on. So we neglect the higher term because epsilon is very small. Y bar y plus epsilon dy bar over d epsilon at epsilon given to be 0. So what can we write this equation for the derivative of the function y? So that will be something y dash plus epsilon dy bar dash over d epsilon given epsilon to be 0 after calculation. So I am writing this as x plus epsilon xi a function of xy, neglecting the higher terms, and this one is y epsilon eta of xy, and this one is y dash plus epsilon eta 1 of xy. Xy and y dash, where you see dx bar over d epsilon is xi of xy with initial condition x bar xy and epsilon 0 to be x. Similarly, dy bar d epsilon equal to eta of xy. Initial condition is y bar at xy and epsilon 0 must be y. And the third equation is for y dash, y bar dash d epsilon is equal to eta 1 xy and y dash, where y bar dash at xy y dash and epsilon 0 should be y dash. So we take these types of transformation, and we are interested here to find the value of eta 1 first. So I am naming this is equation 1, this is 2, and this is 3. So from equation 3, so we are starting from equation 3 again. What is y bar dash? That is dy bar over dx bar and you see what is y bar, that is y epsilon eta of xy from equation 2. And what is x bar? That is x plus epsilon xi of x y. This is from equation 1. So when we apply the operator, so I will get dy plus epsilon d eta and is a function of xy. Similarly, dx plus epsilon dxi of xy. So I can write this y dash as dy by dx plus epsilon d eta over dx 1 plus epsilon dxi over dx, and also I can write it dy over dx plus epsilon d eta dx, and write the denominator is in power minus 1. Okay, now using binomial theorem and neglecting higher power of epsilon, we have eta this 1 minus epsilon dxi dx. So I'm writing further, this will be y dash. So neglecting higher power of epsilon, I have y dash plus epsilon d eta over dx minus y dash dxi over dx. So first y dash will be multiplied with 1, so I will get y dash. Then y dash is multiplied with epsilon dxi by dx, so I get this term, and epsilon d eta by dx with 1, I get this one term. So both have epsilon, so I take the epsilon out of the bracket. Now I have to compare, let's say this is equation 4, so I have to compare this with 3. 3 is y bar dash equal to something, so let's see, y bar dash equal to y dash plus epsilon eta 1 xy of y dash. So if I compare 3 and 4, so I'm writing again, let's say what is 3? 3 is y bar dash equal to y dash plus epsilon eta 1, neglecting higher terms in epsilon. This is 3, and what is 4? That is y dash, y bar dash, y dash plus epsilon d eta over dx minus y dash d xi over dx. This is 4. So when we compare, this value is equal to this, so that means eta 1 is in fact d eta dx, the total derivative of eta minus y dash, the total derivative of xi. This is eta 1, and if I follow the track, then what will be eta 2? Eta 2 will be d eta 1 dx minus y double dash dxi dx, and we can write eta n d eta n minus 1 dx minus y n dxi dx. So this is the general extension formula for eta n. So first order extension, you see, if I have a generator x, xi partial by partial x, eta partial by partial y, so its first extension will be eta 1 partial by partial y dash, and eta 1 can be calculated from this equation. Similarly, second extension will be, this is x1. So if I need x2, then that will be xi partial by partial x, eta partial by partial y, plus eta 1 partial by partial y dash, plus eta 2 partial by partial y double dash, and eta 1, eta 2 can be calculated, eta 1 be calculated from this, and eta 2 can be calculated from this, and so on. So I'm writing the n extension, xi partial by partial x, eta partial by partial y, eta 1 partial by partial y dash, up to so on, eta n partial by partial y n. This is the nth extension of the generator. So now we are in the position to extend the generators and do our calculation for a differential equation. So now I am going to give some examples for the previous lecture. Using this extension, we will be able to verify that the given differential equation is invariant under the given generator, or we can verify the Lie symmetry equation. So for a function, the Lie symmetry equation is this, equal to 0. Given x, when we operate x on function, it gives 0, then f of x is an invariant under x, or you can say it is symmetry equation. So one example is, let's say f of x y is x square y square. This is my function, and let x is x partial by partial y minus y partial by partial x. So you see, if I operate this on x square plus y square, what I will get, x partial by partial y minus y partial by partial x, operate on x square plus y square. So you see, I will get 2xy minus 2xy, and you will see you will cancel is 0. This give me 0. That means this function is invariant under this operator. So you see, this is some verification of the function that it is invariant under the given operator. So we did it in the previous, this is one example for the previous lecture. Let's see another one. If I take x to be x partial by partial y plus y partial by partial x, and function of xy is x square minus y square, you will see that it is invariant. So when I operate it this function, we will see that the first one is 2xy and the second one will give me minus 2xy. It will cancel, so you will get 0. So that means the given function satisfy this equation. That means this is a symmetry generator for this function. This is a symmetry generator for this function. Let's see another one. F of xy to be x over y. We'll take the operator for it to be x partial by partial x, y partial by partial y. So when you operate x partial by partial x plus y partial by partial y on x over y, that will you see give x over y when I operate this term, then minus because of I have to differentiate y, so that is in the denominator, that will be y x over y square, so one will cancel and you see it is 0. That means this function is invariant under this symmetry generators. That means this is a symmetry for it. This operator is generate a symmetry transformation which is equal to this function, or say what we studied xf equal to 0. So that means this is invariant under the given operator. So these are some examples of the function and its generator. So you should be able to check the given generator and function for the symmetry. Now let's take one example of differential equation. Let's say this is my differential equation, x and x plus y and y dash. Let's say it is square. So I'm checking this generator. Let's take this cube. So let's take a generator x partial by partial x minus y partial by partial partial by partial y, and let's check it that it is it a generator for this differential equation or not. So we have to extend it up to second order. So eta 1 is d by dx of eta minus y dash d by dx of xi. So eta is minus y and xi is so I'm writing it, eta in my case is minus y and xi is x. So put it d by dx of minus y dash d by dx of x. So I get it to be minus y dash and minus y dash, so that is minus 2y dash. Now eta 2 is d by dx of eta 1 minus y double dash d by dx of xi, and so it will give me by dx of minus 2y dash minus y double dash, so that give me minus 3y double dash. So the extension now is second extension is x partial by partial x minus y partial by partial y and minus 2y dash partial by partial y dash minus 3y double dash partial by partial y double dash, but I know y double dash is x plus y dash square. So in fact, what is my second extension? X partial by partial x minus y partial by partial y minus 2y dash partial by partial y minus 3 into x plus y dash square partial by partial y double dash. So I will operate this on the given differential equation and see what happened. Is the given differential equation is invariant or not? If it is invariant, then this will be the symmetry generator. Otherwise, y plus y dash square equal to 0. So I will operate x second extension will be operated on y double dash x plus y in y dash square. So you see, when I operate this operator, so the first one will hit this y double dash, so that may give me minus 3 times x plus y dash square. It's come from this term when I operate it on y double dash. Okay, that's correct. Now I will operate x on x. So that means there is a minus sign and x with y dash square. And I will operate it on y. So minus minus will plus. I will get y here and y double y dash square. Okay, now I will operate this on y dash, so that will give me minus 2y dash x plus y, and this minus 2, so that will plus, it will become 4 and y dash become, so 1 y dash is here square. So 2 from here, 2 from the derivative, that is 4 minus and minus become plus, and y dash is here and here you will get that. So is this is cancelling? If yes, then it is symmetry. Otherwise, you see, so we have if this is minus also minus, then it is symmetry, otherwise not. So let's check it again. y, we need to operate on y, so that is 1. This minus and this minus is plus. Yeah, so it is not equal to 0, is not equal to 0. That means the given operator is not a symmetry for the given differential equation. Okay. Okay, thank you.